So far we were discussing limits of functions. So having finished limits of functions, in this new session we will be discussing continuous functions. So what is the difference between a function having a limit and a continuous function? Let us see using an example. Suppose we define a function, say f of x is equal to 3 for every x not equal to 2 and 1 for x is equal to 2. So what is the shape of this function? Let us see using a graph. For every real valued x not equal to 2, the function takes the value 3, and for x is equal to 2 alone, the function takes the value 1. So we can see that for all the other values except x is equal to 2, where the function takes the value 1, for all the other x values the function is assuming the value 3. So if this is 1, somewhere here you will have your 3. So the function is a straight line for the entire other values of x, or for the entire real line except the point x is equal to 2. So here I will draw a hole to show that this is the shape of the graph, or this is the function given. So as we move along this line of, or along the curve showing f of x, we can see that throughout this region we can go through the curve without taking our, or without any gap or without any discontinuity. But when we reach this point, the function suddenly goes down to the value 1, and then from again it goes like this. So that particular point is called the point of discontinuity of the function. But when we look at the limit of the function, we can see that the concept of limit itself says that limit x approaching to f of x is equal to what? So x approaching 2 means x is never equal to the value 2, x is only becoming closer and closer to 2. So it can be either through this side or through this side. And using the epsilon delta definition that we have discussed in the previous session, we can see whenever x approaches 2, the function takes the value 3. It is somewhere here or somewhere here we are looking at. So the function takes the value 3 as x approaches 2, and so this limit becomes exactly equal to 3, whereas the function has the value 1 at the point x is equal to 2. So the limit is exactly equal to 3, but the function's value is different from that of the limit. Whenever we have the function's value and the limiting value to be the same, we will say that the function is continuous at that point. So with that perspective in your mind, we can look at the definition of continuous functions. Let A be a subset of R and C be any point on the domain A. If f is a function from A to R, f is a continuous function at a particular point C. If given epsilon greater than 0, there exists a delta greater than 0 such that whenever x is an element of A satisfying the condition 0 less than modulus of x minus c less than delta, modulus of f of x minus f of c is less than epsilon. So look at this definition of continuity and the previous definition of limits that we have discussed. We can see all the other conditions are exactly the same. The only difference is instead of the limit L, we have the value of the function at that point. So whenever the limiting value is exactly equal to the value of the function, we will say the function is continuous. So this is denoted using the notation limit f is continuous at a point x is equal to c if limit x approaching c f of x is exactly equal to the value of the function at that point c. So, this is the concept of continuity. Now, so that is exactly the definition given. Now, as we have discussed in the case of limits, whenever we have a condition for one particular function, we will look at what happens if we combine two functions, combine one or more functions, two or more functions together. So, if A is a subset of R and f and g are two functions from A to R which are continuous, then f plus g, f minus g, fg and a constant multiple of f, these are all continuous functions. If g of x is not equal to 0 for all x belonging to A, then f by g is also continuous. So, this can be applied for rational functions and so on. So, what does this indicate? F plus g, f minus g, fg and kf are used in some real world situations where two or more functions are combined together to get a new function, because we have seen that we can consider or we can imagine the graphs of polynomial functions, we can imagine the graph of sin x, cos x and so on, but in random real world situations, if we consider or if we draw the graph of a particular function, it can be a combination of all this. Say for example, if we are drawing the graph like a cardiogram, if we are having, then it will be a combination of sine functions, or it can be a combination of cosine functions and so on. And there can be some magnifications also happening for the functions. That is why we need a constant multiple. So, whenever the underlying function is continuous, the magnified or the compressed function also becomes continuous by using this result. So, that is the importance of learning these theorems. So, the proof actually follows from the algebra of limits that we have discussed. It follows by using the triangle inequality and so on. Then we have the next result, composition of continuous functions. So, before learning the composition of continuous functions, let us have a bit more insight to what is continuity. So, we have discussed that limit x approaching c f of x is equal to f of c is the condition for continuity. So, that means suppose we draw a picture something like this, f is a function from A to R, and we have an let v equal to the delta neighborhood of C, delta neighborhood of the point C, then whenever x belongs to the delta neighborhood of C, that means C minus delta, C plus delta, correspondingly f of x is in the epsilon neighborhood of f of C, f of C minus epsilon, f of C plus epsilon. So, this portion is actually being carried exactly to this entire interval somewhere here. So, this is the meaning of continuous functions. Or we can say that whenever x belongs to A intersection V, we have the image or f of A intersection V is a subset of your delta epsilon neighborhood of C, f of C minus epsilon, f of C plus epsilon. So, this is the exact concept of continuity. So, using this concept we can imagine or we can think of the proof of composition of functions. Now, before going to the proof of composition of functions, we can see what is a composition of function. Suppose f is a function from A to R and g is a function from B to R, where f of A is a subset of B. Then we can have g composition f is a function from A to R and g is a function from B to R. So, g composition f will be a function from R to R, or somewhere we can write subset of R to R. So, G composition function we can define like this. So, we can have A to R where you have your f of A, and this is contained inside your B. So, G is defined from B to R. So, we can have G composition f is a function from A to R itself, because f is defined only for A. So, we can have G composition f is a function from A to R. So, we have seen that in this theorem, what do we say? If we have A and B subsets of R and f is a function from A to R is continuous, G is also continuous on B. If f of A is contained in B, then G composition f from A to R is continuous on A. So, why is this theorem correct? Because as we have seen in the previous case, this is your A, this is B, and this is R. If you have a delta neighborhood of C, corresponding images will be in the, because f is continuous, given f is continuous, and so f of C lies in the epsilon neighborhood of, f of x lies in the epsilon neighborhood of f of C minus epsilon, f of C plus epsilon, and since G is also continuous, it indicates that this is taken to the some other neighborhood, say eta neighborhood of G of f of x minus f of C minus eta G of f of C plus eta. So, this follows from the continuity of, this is taken to this interval and this is taken to this interval because G is continuous. So, in effect G composition f is directly from this to this interval. We can combine these two. So, that is the concept behind the composition of functions. So, that is why we can have, if G and f are both continuous, G composition f is continuous. If the discontinuity of one of these holds, G composition f cannot be continuous. So, that is the concept of composition of continuous functions. Now, we have the next result. If A is a subset of R and f is continuous, absolute value of f is also continuous, square root of f is also continuous. So, these follows from the previous result, composition of functions are continuous, square root function is continuous and f is continuous means square root of f is continuous, absolute function is continuous, f is continuous, and so modulus of f is continuous. So, by the previous result, composition of continuous functions, we can see that these two automatically follows. Now, some examples which are very frequently required in real world situations as well as in applications of mathematics is what are or how we can classify the functions based on continuity. So, the main classification of continuous functions consists of the polynomial functions, sine and cosine functions, modulus functions, and there are a few more functions which I have not mentioned here, like rational functions where the denominator is not equal to 0, and many more functions, exponential functions like that. So, the majority or mainly we have to consider the polynomial functions, sine functions, cosine functions and modulus functions at least. So, what are polynomial functions? We know the expressions like x, x square, x cube, the combinations of all this and the multiples of these becomes the polynomial functions. It has a general expression also, a n x raised to n plus a n minus 1 x raised to n minus 1 plus etc. plus a 1 x plus a naught. They are continuous functions because x, x square, x cube, the power functions of x are all continuous functions, and so by the previous result, if f and g are continuous, f plus g is continuous, kf is also continuous, and that results to the continuity of polynomial functions. Sine and cosine, namely the circular functions, are the two trigonometric functions which are the only two trigonometric functions which are continuous. Regarding modulus function, which is a very important function, the continuity of modulus function can be viewed from the graph of the modulus function, or it can be viewed by using the concept of limit of f of x is equal to f of c as well. So, here I will give you a small illustration using the geometrical figure. Modulus of x, the graph is something like this. We can see that on the left side it is minus of x, because modulus function is defined as mod x is equal to minus x for x less than 0, 0 for x equal to 0, and x for x greater than 0. So, on this side it is a straight line. For every x value, negative of that x value, that becomes a positive value. So, that is like this. For x is equal to 0, it is equal to 0, and for x greater than 0, the function is like this. So, it is a continuous function. At every point, the limiting value is exactly equal to the value of the function. So, that is the case of modulus function. So, that is also a very important example of continuous function. Now, coming to examples of discontinuous functions, the main two functions which everyone who is learning real analysis should keep in mind are Dirichlet function and Tomei function. Dirichlet function is a function defined like this. A function f is defined like this: f of x is equal to 1 if x is rational and 0 if x is irrational. So far we were learning the properties of real numbers, the properties of rationals and irrationals. So, you may be remembering the density theorem that we have learned, and using density theorem we have seen that between every two real numbers there is a rational number, and between every two real numbers there is an irrational number also. So, when you plot the graph of this function, we can see that 0 is obviously a rational number, and so the function takes the value 1 at 0. The next point to 0 will be definitely an irrational number, so the function will take the value 0. For 0, this function will take the value 1. For the next value to 0, which will be obviously an irrational number, the function takes the value 0. And if there is an irrational number, the next value will be definitely a rational number. It follows from the density theorem that we have learned. So, this will be 1 at this point. The next point will be an irrational number, next point will be rational, next point will be irrational, next point rational, next point irrational, and so on. So, it is a very beautifully depicted function which is highly discontinuous. At no point it is continuous. We cannot take our hand, we cannot draw this without taking our hand from this. So, 1 0, again 1 0, again 1 0, and like that it will go on. So, this is the Dirichlet function, which is a highly discontinuous function. At no point it is continuous. And the next example is a Tomei function. Tomei function is like this. F is a function again defined from R to R. So, here also f is a function which is defined from R to R. So, Tomei function is defined from 0 1 to R actually, closed interval 0 1 to R. Closed interval 0 1 to R, where f of x takes the value 1 by n whenever x is equal to a rational number of the form m by n. That means x belongs to Q. X is a rational number and 0 otherwise. That means whenever x is irrational, it takes the value 0 as in the case of Dirichlet function, and whenever x takes a rational number, it takes the form 1 by n. So, actually the graph of this function comes like this. It will be something which comes like this downward, because as n tends to infinity, the function will take the value 0, but only at intermittent points, because in between, as I said earlier, between every two rational numbers it will be there will be an irrational number, and so it takes the value 0 there. So, this is also a discontinuous function. So, these two are examples of discontinuous functions, and we can see that there are many other cases of discontinuities, which are removable discontinuity, infinite discontinuity, jump discontinuity, and so on. So, removable discontinuity is the case that we have seen in the first slide or first case. That means if you have a function something like this, actually the discontinuity can be removed if we put the value x is equal to 2 as 3 for the function. So, if the function takes the value 3 at x is equal to 2, this discontinuity could have been removed. But unfortunately, here the function is given to be taking the value 1 at x is equal to 2, and that is why the discontinuity arises for this function. So, if this x is equal to 2 could have been replaced by the limiting value, the discontinuity could have been removed. That is why this type of discontinuity is called a removable discontinuity. Jump discontinuity means for a step function we can see a jump discontinuity. For step function means it is like the integer function or floor function, we can say floor of x. We can see that there is a jump discontinuity there. It will be something like this, the function graph will be something like this. So, at each point the left hand limit is not equal to the right hand limit, and so there is a discontinuity there, limit itself does not exist, and so this is an example of a jump discontinuity. Infinite discontinuity is something like, suppose you have f of x is equal to 1 by x square for this function, at x is equal to 0, the graph will be something like this. So, we can see that at x is equal to 0, the function is taking the value infinity, and here there is no continuity at that point, because the left hand limit, right hand limit are both infinity, but the function is not defined at x is equal to 0. So, these are some of the examples of discontinuous functions. So far we were discussing continuous functions, their properties, some of their properties, what are continuous functions or which of class of functions can be considered as continuous functions, and some examples of discontinuous functions as well, and that is all. So, this is an example of discontinuous function, and thank you.